Welcome back to the Art of Math. Today we will cover chaos theory. So first thing I want to mention is to see the description for tons of links and resources to learn more. The main value of this video, in my opinion, is just to put this topic on your radar, just like in the Fibonacci number video. So take this video and I want to encourage you to explore way more on your own by looking at the massive amount of resources in the description to both save you time as well as direct you to particularly interesting things, at least things that I've found interesting. You're generally not going to find chaos theory covered in sort of like the high school curriculum or the junior high school curriculum, or basically until college or graduate studies. And I feel like it's as important as anything else out there, and it's really fascinating, so that's why I want to put it on your map. Okay, so let's dive in. So what is it? You can look up the technical definition, which actually has 3 conditions, so I won't go into that. Look at Wikipedia, chaos theory, for the details on that. So I'm going to give you kind of a layman description. So chaos theory, according to Wikipedia, is a branch of mathematics focused on the behavior of dynamical systems that are highly sensitive to initial conditions. Another illuminating definition of chaos from Stephen Strogatz's book called Nonlinear Dynamics and Chaos goes as follows. Chaos is aperiodic, long-term behavior in a deterministic system that exhibits sensitive dependence on initial conditions. So that may have been a mouthful. There are sort of 3 terms in there. Aperiodic, so I'm discussing in a second what aperiodic is, but periodic just means there's a set pattern. So it repeats every so often and we can see it. So for example, 175 has a period of 3. Every 3 items it repeats. Aperiodic, by putting that A in front, just means there is no recognizable period. Alright, so that's what aperiodic is referring to. Then we have sensitivity to initial conditions, which we will get into in a bit. And so we have aperiodic, and then we have deterministic. So deterministic means determined. So if something is deterministic, that means once you start something off, it will happen in a way that is set in stone. There is no randomness. So when you think deterministic, it's the opposite of random. All right. So what makes chaotic systems unpredictable has to do with the fact that they are aperiodic as well as nonlinear. So what does nonlinear mean? It means it's not a line. So like, what's an example? Let's take y equals x squared. If you set x to 0, y is 0. If you set x to 2, y is 4. So we've bumped the x up by 2, y moved up by 4. So if this were linear, if I move x up by another 2, this should move up by another 4. Since that doesn't happen, it moves up by 12. That means this is an example of a nonlinear function. So a lot of interesting things are nonlinear. All right. So that has to do a little bit about what it is. Basically, we'll see as we go through, you'll have a better understanding of what it is. Okay, so the origins. Now, at least as far back as the 1880s with the mathematician Poincaré, he was studying the 3-body problem, referring to the astronomical bodies and orbits. He noticed that some orbits neither go off to infinity nor approach a fixed point. Basically, there is some sort of complex behavior that is pretty hard to model. So that was one of the earliest things. And then the field really got its start with Edward Lorenz in the 1960s and then in the 1970s. And he was one of the pioneers of the field. So what he was doing, he was observing weather patterns and modeling weather using some differential equations, which is an area of math. And what did he observe? He observed this pattern in his model. So this is called the Lorenz attractor, but if you look at this, which is like the sideways letter 8 or infinity symbol, this is probably one of the origins of the term the butterfly effect. So it kind of looks like a butterfly, in case you guys didn't know where that comes from. So, and what is this actually doing? This is a loop. So if you follow this data, it kind of evolves and it goes this way, but it doesn't just loop as a figure 8. Sometimes it goes a little here, a little there, and it's not just one loop. There's a lot of loops in here, and they kind of, I don't want to say randomly, but they very unpredictably tend to follow each other. And so to see more of this, definitely look at the links in the description. There'll be a fantastic video illustrating the butterfly effect and the Lorentz attractor in there. So one of the keys to this plot is estimation. Since computers must round numbers to fit them into their memory, the errors eventually add up. So this is why long-term weather prediction, which requires extrapolating from approximate data, not to mention the fact that we have an approximate model, it might not be a perfect model, these errors will tend to grow the farther out you use the model. And so the predictions will become less and less accurate. So Lorentz has a quote, "Chaos, when the present determines the future, but the approximate present does not approximately determine the future." Again, that's kind of saying the same thing as this sensitivity to initial conditions. And the best way perhaps to see that is to look at examples. But if you go back to this Lorentz attractor figure 8, basically that's saying if you start off on a slightly different trajectory, you're not just going to go into that original. Basically, where you start off is going to really determine where you go. So even if you're a little bit off, you're not going to converge to some other pattern. I'll leave it there for now, but in the description, you guys will be able to see that explained very well. So a Lorentz attractor is also an example of something called a strange attractor. So I just want to put that on your radar. So what is a strange attractor? It means that there's these points in these holes over here, and these points, these trajectories, they're not approaching those, but they're sort of hovering around them. So it's very much an attractor. So let's discuss what a normal attractor is. So what is a normal attractor? Think of like a skateboard or a ball. If you put it on a ramp and you just roll the ball down, it will kind of go like do that gravity thing, and then it will settle down at that bottom point. So that bottom point would be a regular attractor because that's where the thing's going to end up, and it's a fixed point. It attracts the ball. However, here it's not a regular attractor because not everything is going to approach it. So the term strange is referring to the fact that there's this chaotic behavior around those attractors. All right. So this sensitivity to initial conditions is something you're probably already familiar with, like I said, by the name of the butterfly effect. So these are kind of referring to similar things. And like the original quote is the butterfly effect is that a butterfly flapping its wings in Brazil can cause a tornado in Texas. That's the famous quote. And like I said, please see that I'll link to a wonderful video in the description of the Lorentz attractor, so you'll get to see like a particle on its actual trajectory and different particles and what's going on in that diagram. All right, so next question. So why is there a butterfly effect? I mentioned this briefly above with the estimation, but let's expand here. Basically, minor changes propagate up the system and cause bigger and bigger changes. So you could think of it in terms of a quick math example. Let's say we have 3.544444445. If we start rounding it, that 5 at the end will round that last 4 to a 5. And if we round on top of that, we're going to basically convert more and more 4s to 5s until we finally get to like 3.545. Then we'll round that to 3.55, which will round to 3.6. Basically, if we're rounding on top of rounding, that will create a bigger and bigger error. So that's what happens when you apply estimation on top of estimation. So whether we're using computers which can't store an infinite amount of digits in precision, or whether we're using rulers and measuring things. For a silly real-world example, let's just say that I left home late, and because of that, I missed the bus, because of which I was late to work, because of which I was fired, because of which I got angry and punched my annoying neighbor, because of which I ended up in jail. Just like those ridiculous insurance commercials you see on TV. So in this case, a minor lateness propagated into a larger event of my going to jail. All right, so I'm going to quote from one of the resources because I thought this was a very enlightening quote. So what makes these deterministic systems unpredictable, referring to these chaotic systems, is their extreme sensitivity to initial conditions. all of this is further complicated by the fact that one can never make a truly accurate measurement of anything. If one were to measure the length of a table, the degree of precision allowed would be limited by their measuring tool. Using a meter stick, for example, can only approximate to the closest millimeter, although the table's length is certainly not an exact denomination of millimeters. Even if you had the very best measuring tool, eventually Heisenberg's uncertainty principle would come into play and make it impossible to make a perfectly accurate measurement. So they're talking about quantum mechanics coming into the picture at the lowest levels. All right, so quick note, this is an important note. Chaos theory is not just the butterfly effect. That's a great start in terms of your investigations, but there's so much more to it. So if you think like, oh, I already know it, that's just the butterfly effect, just, study it a little more. Definitely check out the links in the description. So let's move on. So why is chaos theory important? There's kind of one main thing, which is there's just so many applications, whether it's in math, weather prediction, physics, engineering, you name it. But I want to bring to your attention something that is kind of relevant, but maybe not as talked about. And I want to emphasize it a little more, which is the philosophical angle. That chaotic systems are deterministic, meaning there's no randomness. The behavior, once you set something in motion, it will evolve in a mechanistic way. So like if I add 1 to 2 rather, there's no mystery about whether it's going to be 3 or 4. We know for sure it's going to be 3. All right. So it's deterministic. The behavior is determined. However, it's unpredictable. So that may seem like it's sort of contradictory, but it's not. In other words, if I don't know any math, let's say I'm like 1-year-old, so 2 + 1 has an answer. It's determined. In my case, I don't know what it is, so I can't predict it. But that's not a good example because if you knew enough, you could predict it. So chaotic systems their fate is sealed, in other words, but they're not predictable. I introduced this idea in the Myth of Genius Part 1 video, which you can find on my channel. At the end of that video, I mentioned how free will might have a connection to chaos theory. And so that's why I'm kind of really interested in it for at least that reason, because that's a pretty big deal. Even though, our fate can be sealed, we may not be able to know what it is, so it's sort of still interesting. And that word interesting is, that's really the crux of it. The unpredictability makes things quite interesting. All right. So also in the description, some people are exploring the link of quantum mechanics to chaos theory. So I encourage you to check that out. I think at the end of the day, the best way to understand this profound concept of determinism without predictability is by looking at specific examples. In the links, you will find so many. So there's the water wheel, where basically you drip water into this Ferris wheel of water, and if you drip it at a certain speed as opposed to other speeds, for some speeds it's very predictable, and for other speeds it'll like whirl one way, then it'll whirl the other way, and at some point it just starts doing this chaotic thing where you can't predict what it's going to do. So then there's the double rod pendulum. You're probably familiar with the regular pendulum, but now the pendulum has 2 parts. And that creates a pretty interesting scenario. So that there's just tons and tons of examples, and the best thing to do is just look in the description and the link, and the links will have a ton of great stuff. All right. So, and the point there is for some initial conditions, these systems will behave quite predictably, but for others, very complex, unintuitive, and unpredictable behavior will emerge. So here's a bit of a tangent. I had this question, and many of you might have this question, where like, hey, what about pi? Is pi an example of chaotic behavior? Because we know the digits of pi are set in stone. They're not random. They don't change on us every day. But can we predict them? So actually, it turns out it's not a good example, because I'll put this in the link. There's something called the BBP method, which is the Bailey-Borwin-Plouffe formula. Don't worry about that, but you can see it in the description. And so there's a method to calculate the nth digit of pi. So if you want the 17th digit of pi, there's a mechanism to do that without calculating, let's say, the 16th digit. And the fact that you kind of can jump ahead and get a digit without a previous digit is basically saying that it's not an example of chaotic behavior, because in chaotic behavior, you actually have to run the system to see what happens, so you can't predict ahead. However, while we're on this tangent of pi, a fun fact, at least empirically, the first several million digits of pi appear to be uniform in the sense that each digit appears roughly the same number of times. So that doesn't mean they're distributed randomly, but it kind of hints at, it feels a little bit random. So that's sort of interesting. At least I found it interesting. However, the idea with pi is not totally bogus, because in the links you'll find a little bit on chaos theory and how it might actually be useful in shedding more light on pi. So while pi is not an example of, pi's digits are not an example of chaotic behavior, we can study pi using some of the techniques from chaos theory, maybe. All right. So, how come chaos theory wasn't discovered earlier? This isn't the whole answer, but I'd say largely because computers are recent, and they've been critical in allowing us to make these tedious computations and visualizations, which in turn have showed us all these patterns that were there the whole time. So by hand, even this first Lorentz attractor would be pretty tough to see, or with a primitive computer. So you pretty much need a decent computer program or a pretty evolved state of computers to get far in this field. All right. So here's something that I want to draw your attention to as well. A great question or set of questions to explore when studying chaos theory. Just like in the Fibonacci video, I don't just want to present you guys with a barrage of information. One of my goals is to synthesize that information and give you a bird's eye view so that the rest of your explorations can be more fruitful. Because of this desire, I want to direct your attention to this question that I have and that many of you might have after exploring this topic, and that you may want to think about throughout. So, under what conditions does chaotic behavior emerge? So when does this happen? We said that in all these examples, the water wheel, for some speeds it happens, for some speeds it doesn't happen. And when is pretty interesting. Why? So, by the way, for the when in the resources in figure 8, there'll be something called a behavior map, also related to a phase transition. So if you're familiar with water, when it turns to ice, like solid gas, there's a map that shows you basically as a function of pressure and temperature. So that would tell you the behavior. So that would tell you when this happens. So when you're studying a system, a good question to ask is, when do these interesting behaviors, when does the behavior change? When does chaos emerge? For what parameters? An even perhaps tougher question is, why does it happen? There may not be an answer to that, but it's still worth thinking about. And finally, can we predict when the chaotic behavior will emerge? So that's kind of related to under what conditions. So the way I've written it, these are kind of similar. So what predictions can we make? I'll leave it at that. So here's a little thought experiment. Take it for what it's worth. So here's an idea I have. So sketch a flat surface. So let's say there's a fairly flat surface, but if you zoom in on it, there's actually some jaggedy curves. And this is actually, if you zoom in to a surface, this is friction under a microscope. So the surface is actually not completely smooth if you zoom in far enough. So if you're driving a tiny car or some vehicle over the surface, there might be a slow speed in which you get stuck in all these grooves, and a fast speed in which you sort of have a much smoother ride, or you'd be jumping over them. And maybe a medium speed. So like for a really slow speed, maybe you get stuck and never climb out of it. For a medium speed, you might get a bumpy ride. And that's just a simplified example, but maybe that'll give you an idea of like, oh, so the behavior will change as a function of speed, and you can create a behavior map, like for what set of speeds will something interesting happen, or like will it be a bumpy ride, a short ride, a fast ride, a smooth ride, and so on. All right, so let's move on. So at this point you might be thinking like, okay, I get there's this chaos theory thing, but this is like a math theory, so dude, like what sort of math does chaos theory involve beyond butterflies? So butterflies are great, but what math is there? Well, that has to do with these questions we've just mentioned here, which is, analyzing what the attractors will be and the dynamics of how the system will evolve as a whole. So like finding, if we go back to this Lorentz attractor, figuring out like what will these points be over here and how will, maybe not a specific trajectory, but how the whole set of them roughly will kind of, like will they have this figure eight shape or will they go off really far? So just figuring out some like high level things might be really valuable. So those are the kinds of questions we might explore with the math. And depending on the application, though there's a lot of different math. So one common area of math would be differential equations, which you would typically study after calculus, especially like for weather modeling. All right, so that's on the math portion. So to wrap up, a note on resources. So please check all the resources in the description, or at least as many as you can. But I know a lot of you, are busy, you're busy kids, adults, whatever. And if you only have time to check one, then my recommendation is the first one, which is the Sapolsky lectures. Lectures 21 and 22. He is amazing. So if you don't have too much time, just at least check those out. All right. Finally, the subject of the next video will be fractals, one of my favorite topics. And again, in that the main value will be to kind of compile a list of links in the description and give you an overview of the field. And I just want to make a quick connection before we wrap up this video. Fractals will involve simple rules that will create complex behavior. In the same way, not everything, but a lot of things when you're studying chaos theory, for example, the water wheel, there's not a lot going on. There's just a wheel with some buckets, and there's the speed at which you are putting the water in. So also, I've put this in the description, but check out cellular automata. And that is one of the best examples of these simple rules leading to complex behavior. And they're also an example of chaos theory. So please check that out. You'll see that in the description. And that's going to be our sort of segue to fractals in the next video. I'll see you guys in the next video.